Okay, thanks for coming back so promptly. That's very unusual for an audience this size to get people all back into the room on time, so thank you for that. So we're now, as I said earlier, we're now going to have two further presentations before we break for lunch. But this time we're going to take questions after each presentation. Okay, so these are going to be slightly longer presentations going into a bit more detail, which hopefully will also start to address some of the questions that were raised this morning in a little more detail. So to begin with, we've got a double act going. Lynn McDonald, who is low carbon, flexible plug and play solutions manager. Lynn completed her education, which will become apparent when she starts speaking to you, at the University of Strathclyde, where she graduated with a Master of Engineering degree in electronic and electrical engineering. She's also leading one of our LCNF Tier 2 bids this year, so one of two bids that we're putting in this year, which is involving vulnerable customers and energy efficiency, so codenamed VC. So look out for that one later this year. Previously, she had the role of Telecommunications Workstream Manager for Flexible Plug and Play, but as I say, she's now focusing on leading a Tier 2 bid. And then the other part of our double act is Simon Dunkley, who's the Director of Solutions Architecture at Silver Springs Network. Simon's got a wide remit working with European regulators and the industry to develop smart metering and smart grid applications and legislation, as well as directing projects within Europe. He's got 20 years' experience working in communications around the world, having previously worked for Plessey Microsystems and Nortel Telecommunications, and also as a consultant with Detica. So the title of the presentation is Deployment of a New IP-Based Telecommunications Platform Supporting IEC 61850. Thank you.
Well, good morning. So Sam and I will take you through the journey for Workstream 1 of Flexible Plug and Play. So as you've heard this morning, Flexible Plug and Play is a project that aims to connect distributed generation in an accelerated and cost-efficient manner onto constrained parts of the electricity network. And the project will be demonstrating this through the integration of smart devices, smart applications, and smart commercial arrangements. And in order for these to be successfully integrated, it was crucial that the Flexible Plug and Play project selected an appropriate telecommunications platform. And when undertaking the assessment of which communications system to employ, we explored the key functions that the communication system must support, and furthermore, the key requirements and themes and essence of the project. So beginning with the functions, first of all, the communications platform must be able to operate both independently and in parallel with the existing communications within the network. As you heard this morning, that was the satellite and also the GPRS. Second of all, smart devices, a full suite of them from various vendors will be installed. Therefore, the communication system must be able to support data connectivity both within and between the substation sites, and also address the challenges associated with interoperability. And as Tim explored, when we say interoperability, we're looking for a common compatible data exchange between these devices to take actions and also relay information. As part of the Flexible Plug and Play solution, a smart application in the form of an active network management system will be deployed within our control centre. And this active network management system will be monitoring the real-time network parameters of our network. Therefore, the communications must be able to employ and facilitate the data exchange between the system that's centrally located and the devices that are remote within the field. Moreover, the active network management system will be enforcing control signals onto the generators. So it will be managing the distributed generators' export to allow them to track the real-time export capacity within the constraints of the network. Therefore, the communications should support the cheaper and faster connection of DG onto the network. And if we're looking at this, 5 key themes come out which the communications must be able to support and deliver to. First is around robustness. We are going to be connecting real distributed generator customers. Therefore, we need communications that is reliable and has characteristics that are self-healing. Therefore, if a communications link is to go down, it's able to reconverge on another appropriate link path. Second is around the theme of scalability. We want communications and connectivity to be achieved on any of our distribution network licensed areas. Furthermore, we want it to be easily extended, both in a technical and commercially feasible fashion. To support the faster connection of distributed generation, we also wanted the installation process of the communications platform to also be easy and undertaken in a speedy way. This would support and facilitate the progressive nature of distributed generation connections and facilitate its remote siting as well. A fourth theme is around repeatability, and that's a key factor within the Low Carbon Network Fund. We, as a distribution network operator, obviously trialling and demonstrating the technologies, but we want to ensure that this can be employed and utilised by our other fellow distributed network companies. And lastly, but most importantly, is around the topic of interoperability. As you've heard, we have selected the Open Standard Protocol IEC 650, but the communications platform must be able to first communicate in the data protocols already employed, such as Distributed Network Protocol 3. This is a vital learning point for the project because it's been used widely within the substation environment for integrating devices within the substation, but there's limited use and understanding of its performance between substations. Therefore, this was a unique standard being placed on a communications platform to extend and support their development. During the bid stage, the project, applying these themes and the functions that we were trying to deliver to, identified that we wished to use an internet protocol-based platform that would employ the wide area network that we already have existing within our UKPR networks portfolio, and also utilise in combination with a radio frequency mesh network, which we will refer to the RF mesh network throughout our presentation. When we looked at the market, we identified that Vodafone and Silver Spring Networks offered an end-to-end communications system that would deliver to the needs and have the potential characteristics around robustness, scalability, and interoperability. Therefore, Vodafone, and at the time of the project was Cable and Wireless Worldwide, and Silver Spring Networks became project partners of Flexible Plug-and-Play. And with them, as part of Workstream 1 for the telecommunications platform, we looked to deliver and deploy an IP communications platform by Q1 2013. And this is the contractual obligation we set out with Ofgem under our project direction. To support this milestone, two key evidence components were required. First off, the successful sign-off of the installation and commissioning of the IP communications infrastructure. And secondly, the unique selling point of the project was the results of the communications trials using IEC 650. And just to recall, this is simulated traffic. This is not with real traffic from real devices yet. Now, to give you in context the sort of data connectivity and coverage which we were seeking, here you've got the trial area, which is between Peterborough and March. Within the Flexible Plug-and-Play, we've identified 12 substations, 2 of which are grid sites, which is Peterborough Central Grid and March Grid. And then we have 10 primary substations dispersed amongst the 700 kilometre squared area. To give you a feel, probably the largest distance points between these sites is about 43 kilometres. Not only that, the communications had to set up connectivity between them, but also to the remote connection to the active network management system within Ipswich. As the project is mainly aimed at connecting distributed generation, at the moment we're only going to be connecting new sites from distributed generation as we're setting out new commercial arrangements. Therefore, as part of the design activities, we looked at connecting the potential 16 sites that were under our connections and planning process, which you can see located around. So this gives you an idea of the communications coverage that we're seeking, and I'll now pass you over to Simon to walk you through the design activities that we put in place.
Okay, thanks, Lynn. So Lynn's asked me to go into a little bit more detail on how mesh technology works and how we can achieve the robustness and the scalability that the project needs. So I've got a highly schematic diagram here, but which is based on the FPP project itself. So we've got on the left-hand side here, Peterborough Central Grid, and on the right-hand side, we've got the March Grid. So those are the 2 points of ingress and egress between the mesh network and the communications network backhaul that's provided by Vodafone. So you can see from Peterborough grid over to the March grid, we've got a high-speed line there. We also have high-speed lines from the grid, from the 2 grid stations back to the active network management system, which is hosted at 4 Hamlet in Ipswich. So that gives you, in the backhaul system, lots of route diversity. So then looking at the mesh network itself, what we've got within each of the grid stations are 2 radios here. We call them E-bridges. The ones that are in the substation here are called master E-bridges. And they connect via IP into the router here. So that's the interface point between the 2. And then in the center here, we have all of the various nodes that need to be connected via the mesh network. So essentially, they are the grid stations, substations that Lynn's talked about, and also the generator sites that are to be connected into the mesh. So each of these has a radio. Again, there's an E-bridge in there, which is able to connect automatically to all of the other E-bridges that are around. Now, mesh networking technology has been around for quite some time, but it's generally been used in military applications. And the reason for that is because it's quite expensive, or has been expensive in order to do the processing that's needed to keep track of all of the various network connections that are used by each node. But what we think we've achieved at Silver Spring is to use latest state-of-the-art technology at an affordable price. So on each of these radios, we've got an ARM7 microprocessor, we've got 8 megabytes of RAM, 16 megabytes of flash RAM, and the security associations between each of the devices is handled by dedicated hardware within the radios themselves, because obviously security is an extremely important part of the solution. Also, the radios themselves use frequency hopping technology, hopping for this particular project over 6 megahertz. So that gives you an extremely robust bearer against both deliberate jamming and also accidental jamming. All of the radios are standard-based radios, typically IEEE standards and also ETSI standards, which have been developed over the past couple of years. The underlying networking protocol that's used within the network is IPv6, which is the future protocol which is going to be used in the internet as a whole over the next 5 years or so, because IPv4 addresses are running out. However, we also are able to tunnel IPv4 through the v6 protocol to make sure that we can link in to legacy commercial networks, or corporate networks, I should say. The capacity that we've got on the NICs is huge, so that means we should have plenty of overhead in the future for when we have new applications coming along, and also inevitably when we have to increase the security associated with the solution. And the way that we do that is by uploading new firmware to each of the devices in a secure way. The applications that we're running for the A&M for this particular project are taking most of the data and sending it back to the central A&M system. We anticipate in the future also that there will be more applications where there's local networking between the individual nodes, and I'm sure that's something that the project will eventually be moving on to. So, as I said, each of the nodes fires up and it starts to talk to other nodes that are around, and it establishes secure associations with one another. There's no way that you can just put a radio out there without having the sufficient security on the nodes. And they all talk together and they form a mesh over the geographical area that we've talked about. Generally, by putting a node out there at the endpoints that you want to connect, we find that we generally get a good mesh there. But sometimes we have to augment that mesh by putting an additional radio in there, and that's what we call a relay. And that's basically the same radio, but we put it in a ruggedized form on a utility asset, typically for this project at the top of LV poles. And we've had to deploy a few of those, and so I've got that marked schematically just here. So that gives you good connectivity here. So you can see that any particular node here, as well as having the good redundancy from this point here, you've got many, many different routes to either this side or this side here. So in that way, we can achieve the reliability and the robustness of the network that we're looking for. But the devices themselves are intelligent enough, they've got enough processing power on there to work out the most appropriate route to preferentially send traffic back to the sender. So for this particular node here, it's coming through this relay going back to Peterborough, and this node here is going down here, and it's going out to the March grid. There are various failover mechanisms that we have, both failures within the WAN and failure within the mesh. I'm just going to look at one of them. So let's assume that this node here, which is going through this relay, for some reason that relay fails. And therefore, all of these connections here are lost within a very short period of time, and we'll talk about that in a little bit more detail later on. This node can then understand that it needs to send traffic that way out of the network. It's also able to communicate to the WAN network itself to make sure that any traffic that's coming from the A&M is also sent to it this time now through March rather than through Peterborough. So management of the network. So all of the communications that I've talked about so far has been operational data. So that's data that's coming from RTUs, coming from the frequent use switches, and that's going back into the A&M system. And all of that data remains on UK Power networks at all time. The management of the network, so by management I'm talking about the management of the communications network, also goes over this air interface. However, at the end point, we break it out into a separate device here called an access point to make sure that we don't overload the masters here. There were various other reasons why we use the access point, but I won't go into the details of that. But essentially the data then goes back to our centralized communications management system called Gridscape, and I'll talk about that in a little bit more detail later on. So taking a step back, what I've just talked about is the mesh network here. The way that it connects via the access point and the remote e-bridges is through the local area network at March grid and at the Peterborough Central Station, and then it links into Vodafone's multiple service platform there. The data that then passes over this platform is firstly the communications data, the operational data, which goes down to the active network management server that's hosted at 4 Hamlet in Ipswich. We have the data which is going to the Gridscape server, which is hosted on the Vodafone infrastructure. But also we're linked into the internet itself, which allows UK Power network staff to access the front end of the Gridscape server and be able to manage and monitor what's happening on the mesh network. So just looking in a bit more detail at the individual devices, and if you'd like to come and talk to us later on, it would be great to show you some of this equipment in more detail. So the main devices that we're talking about here, the 16 devices that we've rolled out, are the e-bridges here, the remote and the master e-bridges. They're typically housed within an RTU. They do have to be protected from the environment. They're powered by DC, and that DC normally comes from the RTU itself. And then we run low loss RF cable up to an antenna at the site and try and get that antenna as high as possible. We've got two ways of connecting the communications on the front of it. We've got a serial interface which can convey legacy applications such as, or protocols such as DMP3, and we've got an RJ45 Ethernet connection, which is what we're using on the FPP project for communicating IPv4 and IPv6. The relays are here. They are ruggedized. They're able to be left out in the rain. And as I say, we've put them on the top of LV poles. And Lynn's going to be talking about that in a little bit more detail later on. They're battery backed, so if there's a failure within the network, then they keep going. The antenna is there. And as I say, they make sure that we have a good connectivity in the network. The access point, which is the device that I told you about that's used for conveying the management traffic, looks very similar to a relay. That's here. There are two ways in which we can connect the backhaul from the access point. One is using a cellular 3G connectivity, or by using Ethernet, and that's the option that we've used for the FPP project. As I say, it looks very similar to the relay, but the way that we've deployed these for the FPP project is to mount those within the March and the Peterborough grid and then run low loss cable up to the antenna within the substation. Finally, we've got another device here which is called a field service unit. So that's something that connects via USB into an operator's laptop. And so when the guys are deploying any equipment, or when the guys want to go out and do some investigations into the network, they can use that and they can talk to the devices. So for example, if you've got a router a relay that's 7 meters up in the air, you can talk by radio up to there without having to physically connect into it. So the software that we've got here, we've got two lots of software that I'd like to tell you about. First is Gridscape, so that's the system that's used for managing the data. So basically what it does is it collects the data that's coming back from the devices that are out in the field. What it does is it runs a series of cron-like devices, so processes that are running every 15 minutes or every hour and pulls data back from the way that the network has configured itself, and also looks at the sort of performance that the devices are recognizing that they are achieving. Also with Gridscape, as you can see, we can demonstrate what the connectivity looks like, and there were some pretty pictures there, and again, if you come and talk to us afterwards, we can show you in more detail what's happening there, and also other statistics such as the reliability of the individual frequency hopping channels. The communications tester is the one that's linked, run on your laptop, and it links into an FSU, a field service unit, and that basically allows us to look at the data that's held on those individual devices, and typically what we can then do is see whether there are any problems with that device and also see the other connections that it's making to other devices that are out in the field. So in principle, just using the mesh device themselves, the e-bridges, and a small number of relays and an access point, we can provide canopy-like coverage over quite a large area, and that's what we've achieved as part of the flexible plug-and-play system. However, to get to the optimum design is tricky, and what we have is a three-stage process, or at least a three-design process. What we typically do is we take location data, so that's the geographical locations of each of the endpoints that we have to connect, and also the geographical locations of LV poles, which are candidate poles on which we can put the relays, and we do an initial bench study using an RF propagation prediction tool and come up with an initial design. What we then do is send engineers out to the site to make sure to look at each of those nodes that they've identified and make sure that there's, for example, that the nodes are actually there, make sure there's no clutter somewhere nearby which would disrupt the communications, or to see whether there's actually already some communications devices on that pole, which means that we couldn't mount our equipment on there. So the intelligence that we get back from that goes into the enhanced design, and then what we do is we then we have handed over to UK Power Networks for them to roll the equipment out. We've done testing, and we're going to be talking about that in a little bit more detail in a moment. We test it to make sure that we're achieving the sort of end-to-end performance that our customer expects. And sometimes it's necessary to add one or two additional relays into the design, and that's captured in the final design. So looking at the output that we get from the RF propagation tool that we're using, this is the trial area. So we've got Peterborough Central here, March in the middle here, and the various substations around, and the relays that we've got within the design. So this gives you an idea as to what the likelihood is of achieving connectivity if you're a new generator that wants to move into a particular area. So yellow here is a particularly strong RF signal going through green to blue. So if you're a new generator and you wanted to connect, say, here, then you've probably got a good chance of connecting into the network without UKPN having to deploy an additional relay. If, for example, you wanted to come up here, then obviously we're probably going to have to put a relay or two in there to achieve connectivity. But that's the way we do it. You simply drop a radio in there, see whether you get connectivity, and off you go. And in that way, we can achieve the scalability that we're looking for. Finally, another output from the RF propagation tool is this. This shows a prediction of the sort of meshing connectivity that we'll get between all the individual devices. So you can see that within this particular area, with the number of relays that we've rolled out there, we've got excellent chances of meshing, and that's what we found when we rolled it out. So that's the theory, and at this point I'll hand back to Lynn, who was responsible for the rollout of the equipment.
Working through the different stages of the design, of course, first of all, most of this ownership was by UK Power Networks engineering staff, both within our network operations department and operational telecoms. So first off, taking the initial design desktop assessment, we went out and undertook site surveys, identified any unfavourable components that would influence the performance of the communication system. And then from that, it was tailored into the communications design, and then it was decided where each communications device would be located. As you can see here, there's a few images of the installation work. For the backhaul circuit owned by Vodafone for the connection for the wide area network, router cabinets were put into each of the grid sites with accompanying routers, which of course, unfortunately isn't shown in this diagram. Also for the relays, which really the design activity mainly is placement of relays. Obviously the grid sites and primaries are fixed locations. So the only way to influence the overall performance of the network is actually the deployment of relays in locations where it's sensitive to unfavourable environmental conditions like foliage. Therefore, we undertook a sweep of the locations earmarked by Silver Spring Networks from our grid reference detail from our asset register ellipse, undertook the surveys, determined whether it was feasible and applicable. Some areas where it was unfavourable was the fact of air gun pellets. Therefore, obviously, we've got an antenna, which is a bit like almost like a strip light, so it's an easy target. Some occasions there was a lot of BT work on the low voltage pole, therefore it would not be suitable to put our device up. And we also wanted to make sure it was a clean pole and one that was able to be climbed or get mute access for health and safety terms for the engineers. Also, obviously, each communications device has an antenna to support the communications across the network. Therefore, antennas were dispersed amongst the flexible plug-and-play trial area. Namely, at the grid and primary sites, this was either mounted on the external substation wall, or if not, then it was a wooden pole was constructed nearby and the antennas put on top. Through the design stages of the 13 relays that are deployed and live within the system, 12 of which are located on our own low voltage pole infrastructure. But as a precaution, we decided to install one relay at a tower owned by Vodafone, just to ensure that we got the health links and the performance at an adequate level. Therefore, we have one relay within the west side of the trial area located, which gets about a reach out from both west to east. But our favour would be that all the antennas and smart devices are deployed on our own low voltage pole infrastructure. Main reason being is our engineers know the footprint, we're able to have access, and we also have clear common standards for the work method statements and work instructions to gain access, undertake any diagnostics or remedial work. So moving from installing the kit, as Simon highlighted, there was an optimisation phase. So Silver Spring Networks identified 2 remedial activities, one of which was to change the direction of the antenna. The way it was installed, it was not looking in the correct direction, therefore one of the links, usually we look at for about a 3 redundant path from a device. We're only getting 1, so we just changed the orientation of the antenna and that was improved. Second of all, we relocated one of the relays because it was just even though we're working in the Fenlands area, which is reasonably flat, there was just a wee sunk bit location, so we just moved up 2 poles to improve the performance. And then that completed our final field network design and the deployed communications platform. And moving from that installation, we undertook a series of end-to-end tests. There was 2 components, a subset test, which we did in January, which was on a part completed install of the network. Because we're getting close to the deadline for Ofgem, we wanted to ensure that we're getting sort of familiarisation with the tools that we'd have to employ for the tests and ensure that we're nearing the performance levels that we'd set out to deliver. The testing was covering 3 main areas. First off, around the RF mesh network, which was being delivered by Silver Spring Networks. We wanted to ensure that it was capable of the functionalities and performances that we were seeking to do. This was mainly around the robustness and the self-healing areas. Second off, obviously important for this project was for the demonstration of the Open Standard Protocol IEC 62850. And we wanted to ensure that was demonstrated across the end-to-end system. So that was the wide area network through to the RF mesh network. Lastly, of course, we've got the wide area network element supplied by Vodafone. Now, this is a network platform that we use already within our portfolio. We already have clear service levels and we've already very familiarised with how it works. But this was the first time it was being combined with an RF mesh network and specifically for this application. Therefore, we wanted to test completely the end-to-end and ensure that the dynamic routing which was being employed as part of this communications infrastructure was delivered. This is in the case that we had 2 grid sites and 2 master e-bridges for dual redundancy. So we wanted to ensure that the communications devices could reconverge under different failover modes. So I think Simon and I will just take you through 4 of the key tests. So Simon, I think you're taking the first 2.
Indeed, yes, thank you very much, Lynn. So as Lynn said, there were the 2 sets of testing that we carried out. One was locally at a substation, so we literally plugged into the e-bridge to see what the communications capabilities were from that master e-bridge out to sites. We also looked at end-to-end communications from Fore Hamlet right the way out to the site. So we're running out of time a little bit, so I won't dwell on this for too long, but these are we've got lots and lots of data, did lots and lots of testing, but these are the main KPIs that we achieved. So in terms of the reliability of the network, in terms of packet reliability, because we anticipated that the A&M system itself would be able to handle drop packets, the target for that was better than 90%. We smashed that. We got 99.76%, and that's the sort of reliability that we would be expecting to achieve and do achieve in other networks that are rolled out around the world. The round trip time from Fore Hamlet out to device all the way back again, which could be up to 3 hops on average. Typically, we look at, for the V2 devices, which was the generation of technology that we initially rolled out for the FPP project, we're looking at 50 milliseconds per device. Inevitably, sometimes there is some link layer retries, so that increases from the X times 50 milliseconds. But on average, we are looking at round trip time of 320 milliseconds, which again is well within the 1 second target that was set for us. The throughput for the V2 devices that we rolled out, the devices themselves are, and I forgot to mention this earlier on, are TDD, so time domain duplex devices. They talk one way, then they have to stop and talk back the other way. So the raw throughput is 100 kilobits per second. When we put them into the mesh, the sort of throughput that we achieve out to 3 hops was 30 kilobits per second, and for a single hop was 70 kilobits per second. So we used the capacity pretty well. Looking at those numbers, we've since recently rolled out V4 e-bridges, and things are looking better. We assume that the packet reliability will be similar. The round trip time is more like 200 milliseconds, and the 30 and the 70 kilobits per second for 3 hops and 1 hop respectively is turning out to be 70 kilobits per second and over 200 kilobits per second. So that's again, more than exceeding the requirement that UKPN has set us. Route diversity, we're showing that we've got excellent mesh networking there, so that means that we've got good reliability should one device go down. And the failover time, which Lynn is going to talk about in a little bit more detail now, that's the time for the example where I showed the relay going down, the time for a node to recognise that and reroute traffic through a different egress-ingress point. The target was less than 5 minutes. We achieved less than 1 minute. Lynn.
I think this is yours.
Oh, that's me still, isn't it? I do apologise. Not that slick after all. So I was also going to talk about the 61850 testing. So we've carried out various rounds of testing. Firstly, we carried out some laboratory testing because when we were first rolling this out, we didn't have access to any 61850 capable devices. So what we did was we used a simulation tool called Triangle Microworks. What we did was, and I don't want to go into this in too much detail because we could have a real geek fest here, come and talk to us afterwards and ask for Gordon if you would like to talk more about the way that we handle 61850. But basically what we did was we set it up to work in a SCADA type way, so scanning, polling individual devices to get information back. We also had exception reports, so that's devices sending information in. We also, within the laboratory, cranked up the traffic that was going over the e-bridges to make sure to see at what point the e-bridges started to slow down. We then repeated most of those tests out in the field as well once we got the equipment rolled out. Then.
So just focusing on, obviously, we were demonstrating the protocol of I61850 around the manufacturing messaging specification, but also we also wanted to demonstrate that the communications platform could support the standard network time protocol. And this is important for flexible plug and play because it might be that a distributed generator substation, an interfacing substation, might not have GPS. And of course, we're going to be executing control signals and also collecting network parameters from the field. Therefore, we want to ensure that all components of the project are all synchronized to the same time clock. So this allows us to at least take an accurate recording and audit trail of each of the events taken. Most notably and important to the distributed generator customers will be the timestamp of when curtailment signals are issued and when the local A&M controller undertakes and executes that. Moreover, I think obviously a key factor is because we're dealing with real distributed generator customers, we want to ensure that under certain instances of continuity events, there is some failover modes. Therefore, we obviously looked at the RF mesh network in the instance of master reconvergence and remote acquisition. This is where we rebooted a device and just tested the time when it comes back online, how long it takes back to mesh and associate itself with the network. So as you can see here, the times were quite favourable. For the master reconvergence, we have an average for each of the master E-bridges. Remembering there's 4, 2 at each grid site for dual redundancy, we had about an average of 51 seconds. Around the remote acquisition, we tested this for the worst and best case scenario. Best being 1 hop of the remote E-bridge from the master, that took 24 seconds. And worst case being 3 hops from the master E-bridge, it took about 37 seconds. 3 other failover modes that we successfully demonstrated surrounded the fact if management data connection was to fail at one of the grid sites. So we have an access point at each of the grid substations, and we tested if one were to fail, that through our remote management tool Gridscape, we were still able to see the devices and they would all come back online. So this allows us, from an engineering point of view, and a benefit to our company and organisation, is that we can be sitting in the office and get some indices of how the communications network is performing, and also track pre-fault if there's starting to be degradation in the performance of each communications device. Then around the sort of combination of the wide area network and the dual master E-bridges, we failed over a complete grid site, and it was clearly seen that some remote E-bridges that favoured that one would poison the routes. So remote E-bridges would start to understand not to try and go back to that site. And all the remote E-bridges would reconfigure onto the other backhaul link, which meant that in the purpose for this project, that the active network management system will still have established connectivity with the end devices, and we will also have visibility of the performance of the network. Also, we tested the self-healing capabilities, where we basically purposely took out a relay and a remote E-bridge and identified that a device that was dependent on that route back to the access point or the master E-bridge successfully rerouted via a different path and still was able to communicate to the main backhaul circuits. So, as you've heard, we went through the journey of first design, also then installation, commissioning and testing. And therefore, we successfully reached the milestone under our project direction with Ofgem in the form of a report, which was issued to Ofgem on the 28th of March. And from that, I think there was a clear view of what we achieved. I think, as Soteris highlighted, this project, even though it's a demonstration and trial, we are looking to try and serve it as a business-as-usual service model if technically it's feasible and commercially attractive. Therefore, throughout the process of producing this communications platform, we ensured that we could at least assist in that rapid transition. And this first began with ensuring that we had internal stakeholder engagement. And by that I mean that we had clearly mobilised our experts within the industry and within our company to be able to advise, approve and also do the acceptance of documentation and the infrastructure that we were looking to put out in the network. Because at the end of the day, some of the departments that weren't owning and leading this work would eventually be accepting and managing it ongoing. Second of all, training. Obviously, we had to upskill the flexible plug-and-play team and specific departments within UK Power Networks to ensure that we knew how to use the appropriate tools for testing and that we were able to undertake the installation process ourselves. We also employed common practices, so we followed the processes already within the company around work method statements, work instructions, and adhering to health and safety components. And as highlighted before, installation was owned by our company, so it means that we can undertake this work if we want to scale up. And we also set up a service desk, so we have set up support arrangements, and it's currently in operation, where if there is a fault, we've got ticket handling, which can be mobilised by either organisation, be it UK Power Networks, Vodafone or Silver Spring Networks. Therefore, that appropriately identifies the engineering team that needs to go out and run the diagnostics, go out and do the fault work to get the communications platform up and running. And this will also instill confidence in the fact that we're using real distributed generator customers. I think there's many key learning points to take from this project, and specifically the workstream 1 that we're discussing today. But to highlight a few, there's around the topic of design and install. As a project team and as an organisation, we gained an increased understanding of how an internet protocol-based communications platform operated. I think this was unique in this project because we had a utility and communications providers working side by side, which I think provides an optimal solution. We were able to converse our requirements and ensure the design was dictated and steered in that fashion. And the communications providers were able to tailor and enhance their products to our specifications and also get a product that's more commercially available within the D&O market. Secondly, I think obviously for the communications platform, the initial step is always a desktop assessment. But I think, as I had highlighted before, site surveys, you can't get away from at least some man hours going out to site and doing this sort of environmental terrain and visibility site, because that has a lot of influence and knock-on effect on the network performance you'll get, mainly around foliage. So I think obviously the great thing for this project is this is lasting from now to December 2014. So we'll be able to see the performance of the network amongst all the different seasonal variations. And I think also around the supporting the sort of faster connection of distributed generation. Of course, we were seeking for the installation phase of the Workstream 1 communications platform to also be undertake and also be in a short time scale. And this is clearly demonstrated in the recent swap out that we undertook. Of course, Simon highlighted that the initial installation that we put in was version 2. We've recently done a hardware and firmware upgrade to version 4 to improve the latency and throughput parameters. And we were able to undertake that in 2 days. There was obviously some off-site work, but we had an engineering team out for 1 day for the east part of the network and an engineering team for the west part of the network. So it's clear that this can be managed in a time-efficient manner. And I think mainly, of course, to deliver this as a service support model is how to actually execute support arrangements and ensure this is held and owned by UKPAR networks, and the development of service levels to ensure that this is something that can actually be used and employed in the future as part of our connections business. Around IEC 62850, the project is still quite novice. We're still learning and understanding the integration piece of the key components. But we've started to generate new knowledge and skills, also using KEMA as our experts for advice, where we obviously undertook lab tests and recently the communications trials within the field with Silver Spring Networks and Vodafone. I think lastly, a bit of a celebration for the project is that it was the UK's first primary and grid-level smart grid radio frequency mesh network, which we were closely beat by our own UKPAR Networks project, which we did a year and a half back in Ipswich, which was on the secondary level, so it wasn't the complete grid-level sweep. Secondly, for UKPAR Networks, it was our first deployment of the protocol IE 62850 between the substation sites. And lastly, at the time, and I don't know if it's as relevant for Vodafone, but it was certainly Cable and Wireless Worldwide's first smart grid deployment. So next step, specifically for the telecommunications platform, is that we've obviously tested the communications trials for the protocol using simulated traffic. The next step is basically to use real devices. And the biggest piece that this needs to support is the integration element, which we're undertaking the trials at the moment. Secondly, we've undertaken the version 4 tests for latency and throughput, so we will be publicising our performance levels of the communications platform. I think importantly, which is a theme for the complete project, is around the commercial aspects, is that we will be doing a total cost of ownership of the communications platform that we've actually employed. So this is to identify, obviously we're taking an area of 700 kilometres squared, like a cookie cutter, and trying to understand what that equates to across UKPAR Networks portfolio. So I'll finish there, but if you have any questions, both Sam and I and the rest will be happy to answer them.
Thank you, Lynn and Simon, for an excellent presentation. I hope what you've gained from that is, I mean, this is a field trial. It's an R&D project ultimately, but it involves real commercial generators, so it's got to work. And I hope what you'll have gleaned from that is the thoroughness that's gone into the design concept and the testing, the ongoing testing on the network to make sure this thing really does work. Secondly, I think the repeatability, which was mentioned before, we want to make sure that this is a solution that's deployable not only within UKPAR networks, but across Great Britain by our other D&O colleagues. And very importantly, that we're gaining that learning within the company. So as a power infrastructure company, we're understanding what we need to be able to do with telecommunications systems, so we're not overly dependent. Despite the very valuable contribution they make, we're not overly dependent on any single service provider, that we have that capability built in-house. And I think this is going to be really key going forward in certain terms of the skill sets that we'll need as distribution network operators. So hopefully you gleaned that from the presentation. So we've got a few minutes for questions now before we move on to our next presentation. Can't believe you're so spellbound that you can't. There's one question over there, thank you.
Hi there, I might have a few.
One at a time, please.
Yep. Nick Woolard from JRC. One of our many tasks in life is to manage the radio channels for the energy networks. And so I've got some radio channel related questions. Well, first of all, I noticed that they appear to all be omnidirectional antennas.
That's correct.
Not the most efficient way of doing it. Does it have to be omnidirectional, or are you thinking maybe later of using directional antennas, or would that just be too expensive? I guess that it would be. But I'm just trying to minimise the number of channels that you need, you see.
I think probably to justify the reason for this project, maybe on the omnidirectional selection, is that as a project, we obviously were looking to try and cover a 700 kilometre squared area. There's a clear challenge is that we don't know where the distributed generator customers will be connecting. Very much it's influenced on their network planning, them being awarded the planning permission, and secondly, if they also get the bank funding as well to pursue. So we had to design a communications platform that's almost set up to connect a distributed generator anywhere within that footprint. So the approach in the design was a canopy approach. So this was almost trying to make an umbrella cascaded over the 700 kilometre area. So the point of omnidirectional is it means that, for instance, if I'm here at Grid Substation site, and you've got Simon there as a new generator, I'd be able to at least connect reasonably within the distance. I think obviously we have used in the past directional antennas, and obviously that gives you improved performance and see-through, and you can also ensure that there's no foliage, there's no other satellite dishes or communications devices that can cause interference. But I don't know if from Silver Spring Networks, if you've got previous examples from your network using directional antennas?
I'm not aware of experience that we've got of using directional antennas. If anybody from Silver Spring is here that would like to contradict me, that's fine. But I think what you have to understand is this is a different way of approaching the design of networks. So the whole strength of using a mesh network is that you have diversity of connections. So if you're using a traditional SCADA system with a Yagi antenna that's pointing point to point, then that is relatively vulnerable. So if something gets in the way of that, then you've lost the link to that particular station. By using mesh networking technology and using an omni, then it means that you've got lots of ways in which you can go out, and in that way we achieve the robustness that we're looking for.
Okay, thank you. You've answered that question.
So before you ask the next question, are there any other questions that have emerged during that brief interval? If not, there is one here. So I'll come back to you if we run out of further questions. Just one here, please.
Yeah,
Just wait for the microphone.
From the University of Birmingham. So basically, I'm concerned about the long-term deployment of such devices. So what's the estimation of the costs if in the future, maybe one day, you want to replace all the old-fashioned devices by these smart devices? Have you ever got any figures?
So specifically to the communications platform, there will be an output on the total cost of ownership. So that's an assessment that's being undertaken at the moment. I think we've got a clear contractual view of what we've spent to date and the sort of lock-in that we've got till December 2014. And obviously those costs are slightly skewed because this is a sort of funded project and there is benefit in kind contribution. But the total cost of ownership model that we will be completing with Silver Spring Networks and Vodafone is a spreadsheet where we can influence different scenarios. So that takes into account both the connections that needs to be achieved, also the maintenance and life schedule. But you mentioned smart devices as well. It's about the total cost of ownership.
So basically, my definition of smart devices is basically all these IEDs are smart devices.
Okay.
So actually, the devices you are using in your project.
Yes. So I think, as Stairs highlighted this morning, there's a strategic investment model that will be executed for the project as a whole. So that will take into account the different scenarios of deferral of network reinforcement and deploying the smart arrangement, which would include smart devices and the smart applications. But at the moment, we do not have those figures. The strategic investment model is still being executed as we speak.
If I could add to that, so the reason why we think using IP technology, IPv4 and IPv6, is because that is a de facto standard that's around the world, and that's going to be around for the next 20 or 30 years. So the underlying communications protocol is going to be robust. In terms of the higher levels in the stack, we can always upgrade what's in there using firmware. So we do have the functionality to upgrade both the firmware within the IEDs themselves and also within the NICs on the e-bridges. So the network interface cards on the e-bridges.
Okay, so I think we've got time for one more question. Thank you. Can we have a microphone over here, please?
Hi, Chris Paul from Parsons Brinkhoff. It's a bit of a clarification or confirmation as well. From what I've gleaned so far, you've got the network A&M system sat with the NMAC up at the control centre, and the NMAC is using DMP3 down to the grids and primaries. And just to confirm, you're using 61850. The A&M is operating separate, but data sharing with the NMAC. You're using 61850 from the control centre A&M all the way down to your generators, effectively.
Yep, that's correct.
So you've stepped outside of the traditional 61850 just in the substation.
Yes. So and that's something that was obviously a big selling point. It's unique for our learning and has obviously the key challenges associated with it, and through the development of the products with the vendors. So we're using IEC 61850 to establish data connectivity both within and, as you'd highlighted, the extension between substations and then over to the active network management system located within the control centre.
Okay. I was thinking of like the 6870-104 IP, which is quite traditional, well, is becoming more and more popular as a control centre to substation, replacing 101, but yeah, okay. Interesting that you've actually used the 61850.
Yep.
Okay, so I think we should move on. There may be time to ask further questions of Lynn, Simon, after the next presentation. So thank you very much, Simon and Lynn. I think that was extremely illuminating. Thank you. I certainly learned a lot.